Amid the cold sky of Moscow, one structure rises like a giant needle piercing through the gray clouds. It is the Ostankino Television Tower, an engineering symbol of the Soviet Union and once the tallest structure in the world when it was completed in 1967. Standing more than 540 meters tall, Ostankino does not merely touch the sky. It turns height into signal, carrying images and sound to millions of people. But how could such a slender tower stand firm against powerful winds, freezing temperatures, and the immense weight of its own structure? And how did engineers transform a concrete mass more than half a kilometer high into a structure that is both stable and elegant on Moscow's skyline? In this video, join Mandarin Tech as we explore how the Ostankino Tower was built, an engineering icon that has stood for decades and become one of the boldest achievements in 20th century construction. In the late 1950s, Moscow entered a moment when television was no longer just sound and images broadcast from a few studios, but had become the new pulse of urban life. Programs were increasing, transmission demand was growing, while the Zhukov Tower in Shabalovka was no longer capable of carrying signals far beyond the expanding capital. Moscow needed a new structure, taller, stronger, and complex enough to carry the entire radio and television broadcasting system of a superpower. But to create it, Soviet engineers had to spend nearly 7 years, under the leadership of Nikolai Nikitin, the structural engineer behind the idea of turning Ostankino into a giant prestressed concrete tower. From the first batches of concrete beneath the ground, the large supports around the base, to the tower shaft rising section by section and the antenna assembly being lifted in the wind at a height of more than half a kilometer. Every step demanded almost absolute precision. Ostankino quickly became a conquest of height through concrete steel and bold engineering thinking. The story began in 1960, when Ostankino was chosen as the site for the foundation of what would later become the tallest television tower in Europe. However, the ground here consisted of sandy clay with fine sand, which was prone to compression and settlement, while the solid rock layer lay at a depth of about 40 meters. Therefore, the engineers decided to place the tower on a shallow decagonal foundation, expanding the load-bearing area to distribute the weight of the entire structure across multiple support points. From that foundation, 10 concrete supports began to rise around the base. Each support was formed from large reinforcing steel frames, fabricated in 2 halves, placed onto a temporary metal structure, aligned precisely with the design axis, and then welded to the starter bars below. Because the supports were curved and changed shape with height, the formwork had to be installed in layers of about 1 meter, wrapping precisely around the internal frame. Concrete was then poured from suspended scaffolding and compacted with vibrators on both the inner and outer faces to form dense load-bearing blocks. Thanks to construction teams working in rotating shifts day and night, the support system was erected in about 1 month. When the 10 supports were completed, the site moved on to the load-bearing cone, a transitional concrete mass that locked the entire base system into one unified structure. This cone narrowed gradually as it rose, so the formwork had to be adjusted continuously to maintain the correct design curve, allowing Ostankino's wide base to transition smoothly into the slender tower shaft above. Inside, the reinforcing frames formed a spatial skeleton with circular openings to reduce weight while still maintaining stability. A concrete layer about half a meter thick was poured around the steel system. At an elevation of about 16.5 meters, a monolithic reinforced concrete slab was constructed to increase the stiffness of the base. From this point, Ostankino was no longer a set of separate supports, but had become a solid foundation block, ready for the tower shaft to rise into the Moscow sky. After the load-bearing cone closed in, to construct the main shaft, the engineers installed a special self-lifting system around this structure. A suspended construction site with a working platform, a concrete transport hoist, material lifting equipment, and a large screw mechanism at the center. This mechanism had a lifting capacity of about 230 tons, with a screw shaft 7 meters long and 280 millimeters in diameter, enough to pull the entire system upward after each construction cycle. concrete was mixed at ground level, lifted upward by a specialized hoist, and then transferred through a distribution hopper to the construction position. After each cycle, the tower shaft rose by more than 5 meters. In this way, over about 17 months, a giant concrete axis gradually rose into the Moscow sky, but concrete itself was still not enough to resist the bending force of the wind. Therefore, when the tower shaft reached an elevation of about 195 meters, the engineers began inserting high-strength steel cable bundles inside it. Each bundle had a diameter of about 38 millimeters, was test-tensioned on the ground, and was then threaded through prepared openings in the inner ring structure of the tower shaft. Each cable bundle was pulled upward by a winch, guided into the correct design path, and then tensioned with hydraulic jacks from the lower support cone area. In total, about 150 steel cable bundles were installed and tensioned inside the Ostankino shaft, forming a hidden rib system that tightened the concrete mass from within. Thanks to this, the tower shaft not only rose higher, but also gained enough strength to resist vibration and bending forces as wind swept across the Moscow sky. After the tower shaft was completed, Ostankino was still missing the most important component of a television structure, the metal antenna assembly. This component weighed about 320 tons, consisting of 18 cylindrical sections, each section ranging from 6 to 10.5 meters in length, with some sections weighing up to 24 tons. To reduce risks at height, the antenna sections were trial assembled on the ground, and the radio equipment was also checked before being lifted. The engineers divided the process into 2 stages. First, a 25-ton crane at an elevation of about 385 meters lifted each section onto a temporary cantilever platform. Then, the component was moved into its correct design position and fixed with clamps and bolts from both the outside and the inside. The lower part of the antenna shaft extended about 10 meters into the tower shaft, creating a solid connection with the concrete mass below. The most difficult part was the final section, when the long and heavy component had to be aligned amid low clouds, strong winds, and limited visibility. At one point, it could not be placed onto the intermediate platform and had to be transferred to the self-lifting crane while still hanging suspended in the air. The entire antenna installation process lasted 76 days. 76 days of controlling steel, wind, verticality, and every joint at a height of more than half a kilometer. When the antenna was installed, Ostankino also entered the stage of transforming from a giant concrete structure into a facility capable of operation. At a height of about 325 to 360 meters, the restaurant, technical floors, and transmission equipment were installed around the tower shaft using ring-shaped steel structures, helping distribute loads evenly and adapt to wind and temperature at high altitude. Inside, elevators, stairways, cable routes, and equipment rooms were gradually completed, turning the hollow space inside the concrete shaft into a complex operational network. When the broadcasting, control, and transmission systems were connected to the antenna assembly above, Ostankino was no longer just a tower standing in the Moscow sky, but had become a giant communications machine ready to deliver signals to millions of people below. At a height of more than 540 meters, Ostankino also became a natural lightning point for Moscow. Therefore, the lightning protection system was integrated into the tower structure, helping safely conduct electrical current down to the ground when lightning struck the spire or the body of the structure. From a broadcasting mast, Ostankino also became a giant shield against thunderstorms over the capital's sky. On November 5, 1967, the Ostankino television tower was put into operation, coinciding with the 50th anniversary of the October Revolution. From that moment, the structure standing more than 540 meters tall was no longer a vast construction site, but became Moscow's new transmission center, delivering radio and television signals to millions of people. When completed, Ostankino was once the tallest freestanding structure in the world, a testament to the organizational capacity, calculation, and construction capability of Soviet engineering. But its value did not lie only in records. From a site in the north of the capital, people had built a symbol of the age of mass television, a place where concrete, steel, and willpower came together to rise above the ground. More than half a century after it entered operation, Ostankino still holds a special place in Moscow's urban memory. It is no longer seen merely as a broadcasting tower, but as a landmark of an era when engineering was used to expand vision, connect millions of people, and shape the rhythm of a modern city. Amid the new structures that continue to rise, Ostankino's slender form still stands like a straight line connecting the ground, the sky, and the engineering pride of an entire generation. After Ostankino, the race to conquer the sky with transmission towers moved on to a new symbol, Tokyo Skytree, where Japanese engineering turned height into earthquake resistance, communication, and urban identity. Tokyo is one of the largest megacities in the world, where more than 35 million people live across an urban region that has continued expanding for many decades. For many years, the Japanese capital's television broadcasting system depended primarily on Tokyo Tower, a structure rising 333 meters that was once sufficient to cover the entire area when the city's skyline was still relatively low. But as Tokyo entered the 21st century, its urban spatial structure began to change rapidly. High-rise buildings kept rising one after another, weakening signal transmission, especially when Japan shifted to digital terrestrial television broadcasting, which required a far higher level of signal stability than before. And Tokyo Skytree was the answer, a superstructure rising 634 meters, becoming the third tallest freestanding structure in the world, with an observation deck at a height of 450 meters designed to ensure stable broadcasting coverage across a range of up to 100 kilometers around the greater Tokyo area. Japan lies on the Pacific Ring of Fire, one of the most seismically active regions in the world. On average, the Tokyo area records around 1,500 tremors of varying intensity each year. For a structure rising to 634 meters, seismic motion not only causes lateral displacement in the tower body, but also creates the risk of triggering resonance between the ground and the structure if not properly controlled. To limit the overall vibration of the structure, Tokyo Skytree uses a central concrete core called Shinbashira, a structural solution inspired by traditional Japanese pagoda towers. This concrete core has a diameter of about 8 meters and extends to a height of around 375 meters inside the tower body. Within the first 125 meters measured from the foundation, the Shinbashira core is directly connected to the outer steel structure in order to increase the overall stiffness of the lower part of the tower. Above that elevation, the concrete core is no longer rigidly connected, but is linked to the steel structure through an oil damper system, allowing the two structural systems to vibrate out of phase when an earthquake occurs. This phase difference helps cancel out part of the vibrational energy transmitted through the tower body. Calculation models and tests show that the Shinbashira system can reduce the overall displacement of the structure by up to about 50% in the event of a strong earthquake. In addition to the central core system, Tokyo Skytree also uses 6 rubber seismic isolation bearings placed at the base of the concrete core. These isolation bearings are about 1.4 meters thick and act as a flexible isolation layer between the central core and the foundation. When seismic shaking occurs, the rubber bearings deform elastically to absorb part of the seismic energy before it is transmitted to the upper part of the structure. Thanks to the combination of the Shinbashira core, the oil damper system, and the foundation seismic isolation bearings, Tokyo Skytree is able to maintain operational stability even in the face of major seismic shaking in the Tokyo metropolitan area. When Tokyo Skytree officially began operation in 2012, this structure not only replaced Tokyo Tower in the terrestrial television broadcasting system, but also restructured the entire signal transmission capacity of the greater Tokyo region, the largest urban area in the world, home to more than 35 million people. At a height of 634 meters, Tokyo Skytree's broadcasting antenna is capable of covering a radius of around 100 kilometers, allowing digital terrestrial television signals to be transmitted reliably, even in a dense urban environment filled with thousands of high-rise buildings. However, the role of Tokyo Skytree does not stop at television broadcasting. In a country that is frequently affected by major earthquakes, powerful typhoons, and regional-scale natural disasters, maintaining continuous information and communications transmission plays a vital role in the functioning of the entire urban system. Tokyo's Skytree was designed as a communications infrastructure capable of maintaining stable operation even when the city faces emergency situations, from major earthquakes to widespread power outages. This is not a structure built merely to set a height record, but an engineering solution designed to ensure that even in a city located on one of the most seismically active regions on the planet, the flow of information can continue operating reliably every day. From the sinking mud left behind by the old Tokyo Bay, it rose into a superstructure that tears through the skyline at a height of 634 meters. Tokyo Skytree is not simply a record breaker in height, but a steel-strong statement from the field of structural engineering in the face of nature's brutality. Beyond the dry numbers of steel and concrete, this tower stands as the greatest proof of Japan's philosophy of building. Modern engineering is not created to confront nature head-on, but to understand it, adapt to it, and protect human life against the harshest limits of the planet. By this point, you probably already have a complete answer to the seemingly insane question raised at the beginning of the video. Which technology in this superstructure impressed you the most? Leave a comment and let Mandarin Tech know. And if you love decoding the complex infrastructure that quietly keeps the world's megacities running, do not forget to like the video and subscribe to the channel.